In this lecture, we're going to look into the definition of uniform flow, conveyance of the channels, and how to calculate or determine the normal flow depth. So first of all, what is uniform flow? A flow here is said to be uniform if its property remain constant with respect to distance. In other words, along a channel, if you take any 2 points, the properties is the same at both these points. The property here actually refer to the flow depth and also the cross-sectional area. So, since Q equal to AB, if the flow is uniform between the two sections, the Q or the discharge here should be a constant. So from there, it follows that in uniform flow, the velocity at section 1 should be equal to the velocity at section 2. So, in other words, for a uniform flow, the depth of flow, area of cross-section, and velocity of flow remain constant along the channel. This slide here shows the features of uniform flow. As mentioned earlier, the depth, water area, velocity, and discharge at every section along the channel should be constant. And another features is the energy line, water surface, and channel bottom are all parallel, or in other words, they all have the same value of slope. Uniform flow is considered to be steady only. Unsteady uniform flow is practically non-existent. However, in natural stream, even steady uniform flow is very rare. Despite this, to make our computation easier, we normally assume that the flow in the natural streams are uniform. The results obtained are generally satisfactory. This slide shows the establishment of uniform flow in a long channel under three different conditions. The figure on top shows the condition under subcritical slope. Under this condition, the flow depth actually coincides with the normal depth line, NDL, and under this condition, the normal depth line is higher than the critical depth line, CDL. In the middle figure, the establishment of the uniform flow under the critical slope condition, the normal depth line coincides with the critical depth line and also with the flow depth. While for the last figure at the bottom, under the condition of supercritical slope, the critical depth line is higher than the normal depth line, which coincides with the flow depth. In terms of the calculation of the velocity of a uniform flow, most of the practical uniform flow formulas can be expressed in the following general form, where V is the mean velocity equal to C, which is the factor for the resistance, multiplied by R, which is the hydraulic radius to the power of X, and S, which is the energy slope to the power of Y. An example of this form of formula is the Chasey formula. Chasey formula was developed in the year 1769 by a French engineer, and it can be considered as the first uniform flow formula. The chassis formula is expressed as V equal to C multiplied by the square root of Rs, where C is a factor of flow resistance called the chassis C. Many attempts have been made to determine this chassis C value. For example, attempt by Gangulat and Kutter in 1869, Bazin 1897, and Power in 1950. However, a more well-established and popular formula is the formula developed by an Irish engineer named Robert Manning in the year 1889. This formula is called the Manning formula, and it has a form of V equal to 1 over n R power 2/3 square root of S. The n here is the coefficient of roughness known as the Manning's n. Because this equation is quite simple and produces satisfactory result, it is quite useful in many practical applications and are most widely used uniform flow formula for open channel flow computations. In terms of the conveyance of channel section, the discharge of uniform flow in a channel can be expressed as the product of the velocity and the water area, or in other words, Q equal to VA. As we have seen earlier, V can be expressed in the form of C R to the power X and S to the power of Y. However, if we take K equal to CAR to the power of X, then the expression can be simplified to become Q equal to KS to the power of Y. The term K here is known as the conveyance of the channel section. If the Manning formula is used, then the K will be in the form of 1 over n AR to the power of 2/3. Then from there, the discharge Q will be equal to 1 over n AR 2/3 square root of S. This form is what we call the Manning's formula. To analyze open channel flow, it is usually necessary to know the normal depth. Normal depth is the depth of flow in a channel when the slope of the water surface and channel bottom is the same and the water depth remains constant. Normal depth occurs when the gravitational force of the water is equal to the friction drag along the channel and there is no acceleration of the flow. For a given channel section and specific bottom slope, only one discharge is possible for a given normal depth. This chart can be used to find the value of normal depth for various types of shapes such as rectangular, round, and trapezoidal shape with various subslope value. To use this chart, first we need to calculate what is the value of AR to the power of 2/3 divided by B to the power of 8 over 3. B here is the bottom width of the channel. Once we manage to find this value, then we can go to the horizontal axis of the graph, and from there we identify the value that we calculated and pull a straight line up until we touch the shapes and the value of the shapes that is required, and then from there we can pull a horizontal line to touch the vertical axis. From there, then we can read what is the value of yn over b. Yn here is the normal depth. But if we want to find yn directly from the vertical axis, we need to multiply whatever value that we get from the vertical axis with the bottom width b. Only then we can get the value of yn. For example, compute the normal depth in a trapezoidal channel having a bottom width of 10 meter and side slopes of 2 horizontal to 1 vertical, carrying a flow of 30 meter cube per second. The slope of the channel bottom is 0.001 and n is given as 0.013. So first, we list out what are the details given in the questions. So Q is given, N is given, the bottom width B is given, as well as the side slope 2 and also the slope of the channel. From there, then we can follow this procedure to calculate the yn. So to calculate the yn, like I mentioned earlier, we need to calculate what is the value of ar to the power of 2/3 divided by b to the power of 8 over 3. Actually, this expression comes from the Manning's equations. Q equal to 1 over n ar to the power of 2/3 square root of s. So if we rearrange this Manning's equations expression, then we can get the expression of nq divided by c. Here is, we consider it as 1 because from the Manning's equation 1 over n, so that 1 is actually equal to the value of c. So if we calculate the nq divided by c s to the power of 1 over 2, substituting all the given value given in the question, we will get the value of 12.33. So from there, your ar 2/3 actually is equal to 12.33. So if you want to find the value of ar to the power of 2/3 divided by b to the power of 8 over 3, then this will get you as 0.026. Since this is a trapezoidal shaped channel, we need to go to the line representing the trapezoidal shape with a side slope z equal to 2. So from there, we can pull the value of the horizontal axis 0.026 until it touches the line or the curve for the trapezoidal shape of z equal to 2, and then we read the vertical axis, which will give you the value of yn over b equal to 0.11. So from there, your yn will be equal to 0.11 multiplied by the b, which is 10, which will get you as 1.1 meter. With that, I end the lecture for this slide. Thank you.